In this video, we will be discussing design of pulmonary parenchyma, part 2. We will be covering lung and alveolar septal mechanics, tissue design, and gas exchange surface. In first section, we will discuss parenchymal mechanics and tissue design. Lung as a viscoelastic structure. Lung is not a purely elastic organ. It behaves as a viscoelastic structure, meaning its mechanical response depends on both elastic properties and time-dependent behavior. Elastin provides recoil, collagen prevents overdistension, and surface tension contributes to total recoil force. Components of lung recoil. The total recoil of lung is the sum of two major components: elastic forces of connective tissue and surface tension at liquid interface inside alveoli. Pressure volume behavior. Compliance is defined as change in volume for a given change in pressure. Because a lung is non-linear, compliance varies depending upon lung volume. So compliance C is given as delta V by delta P, where C is the compliance, delta V is the change in lung volume, and delta P is the change in transpulmonary pressure. Fiber recruitment with inflation. At lower lung volumes, elastin fibers provide most of the recoil. As lung inflates further, collagen fibers are recruited. Because collagen is much stiffer, the lung becomes less compliant at high lung volumes. Radial traction concept. The elastic network of lung exerts radial traction on small airways and vessels. This outward pull keeps them open. When this support is lost, as in emphysema, airway tend to collapse. In the second part of this lecture, we will be discussing micromechanics of alveolar septum. Structure of alveolar septum. The alveolar septum is composed of epithelial cells, endothelial cells, and a thin interstitial matrix. Within this matrix lies a network of elastin and collagen fibers that provides structural support. Three-dimensional fiber network. The connective tissue fibers form a three-dimensional lattice that surrounds alveoli and connects multiple units. This network maintains alveolar geometry and transmits mechanical forces throughout lung. Septal behavior during inflation. As lung inflates, alveoli expand and septa become thinner due to stretching of fiber network. During deflation, the septa thicken and alveoli shrink. These changes are reversible. Surface tension in alveoli. The fluid lining alveoli creates a surface tension which contributes to collapsing pressure. According to law of Laplace, the pressure required to open alveoli is directly proportional to surface tension and inversely proportional to its radius. P is equal to 2T by R, where P is the collapsing pressure, T is the surface tension, and R is the radius of alveolus. Role of surfactant. The surfactant reduces surface tension in alveoli. This stabilizes alveoli of different sizes, improves compliance, and prevents collapse, especially at low lung volumes. In last section, we will be discussing lung as a gas exchange surface. Structural design for gas exchange. The lung is structurally optimized for gas exchange. It provides an enormous surface area and extremely thin barrier between air and blood, allowing rapid diffusion of gases. Components of air-blood barrier. The air-blood barrier consists of alveolar epithelial cell, basement membrane, and capillary endothelial cell. This structure is extremely thin, minimizing the distance gases must travel. Determinants of gas flow across membrane. The movement of gas across membrane depends on surface area, pressure gradient, and thickness of barrier. The gas flow increases with greater surface area and pressure gradient and decreases as the barrier becomes thicker. Functional advantages of lung design. The structural organization of lung with thin septa, large capillary surface, elastic fiber network ensures efficient ventilation, uniform inflation of alveoli, and highly effective gas exchange. The lung mechanics and gas exchange functions are closely integrated. Elastic recoil drives ventilation, septal structure maintains stability, and thin barrier allows efficient gas exchange. In summary, lung is a viscoelastic structure with strong mechanical interdependence. Recoil results from both tissue elasticity and surface tension. The alveolar septal network provides strong structural support, while large surface area and thin barrier enables efficient gas exchange. This is a summary diagram of all concepts we have explained earlier. In the first part of diagram, we can see the mechanical dependence of alveoli. Alveoli are mechanically linked through shared septal walls and a network of elastin and collagen fibers. When one unit expands, it pulls on its neighbors, reducing radial traction. This interdependence stabilizes alveoli and ensures uniform lung inflation. In the second diagram, we can see the air-blood barrier and gas exchange occurs through an extremely thin air-blood barrier formed by alveolar epithelium, basement membrane, and capillary endothelium. Oxygen diffuses into blood while carbon dioxide moves in opposite direction, making lung highly efficient for gas transfer.